A warm welcome to all the viewers. We are Group 3 and we will be discussing image evaluation in computer and digital radiography. On to our next slide is our topic outline. Firstly, we will be discussing about the evidence of appropriate exposure level, following by the exposure indicator range, noise, computer noise, electronic noise, material model, quantum model, contrast, recorded detail, artifacts, patient, equipment, exposure, processing, and lastly, the Moore effect. Before I start my topic, let us all familiarize ourselves with the definition of exposure indicators. So, exposure indicators or EIs are the only indicator of correct exposure technique in digital X-ray imaging systems, but also it is the use of such indicators that remains largely unexplored in a South African setting. With exposure creep in the digital radiography age being a worldwide phenomenon, this study investigated radiographers' familiarity and use of EIs. By then, it provides insight into current exposure technique practices in this setting. So, what are the methods they use in that? So, it's an explorative and descriptive quantitative study that was conducted at 10 randomly selected radiography clinical training facilities in Gauteng, South Africa. And the study used a questionnaire consisting of 26 questions based on familiarity with the use of EIs and radiographers' attitude to ionizing radiation. And as a result, there's a response rate of 49.3% achieved. And the result shows a low number of respondents, which is 54.3%, and had a perfectly correct understanding of the exposure indicator. And only 55.7% of respondents made correct use of the exposure indicators. So in conclusion, it is observable lack of familiarity and use of the exposure indicators suggests that improvements could be made to the training radiographers receive on digital imaging systems. Moreover, radiographers need to be vigilant against making decisions in digital radiography using knowledge that may relate exclusively to analog radiography. I hope that it gives you a slight idea about exposure indicators. So here on the next slide is a further explanations about exposure indicators. On the first bullet, X-ray equipment has evolved steadily since Roentgen's discovery in 1895, and most recently the transition from analog to digital radiography. The resultant images in analog radiography unequivocally provided discernible appreciation of exposure techniques. So on the other hand, the wide dynamic exposures latitude in digital radiography created a dearth in observable cues of exposure techniques. Therefore, high-quality X-ray images may be obtained at 500 times the exposure technique that is necessary to obtain an optimum quality image. Hence, knowledge learned about exposure technique from analog radiography can no longer be applied to digital radiography. Looking at the X-ray image alone will not provide information about exposure technique. On to the next bullet. So while the wide dynamic exposure latitude is indicated in literature as an advantage of digital radiography, there has also been evidence to its augmentation of exposure creep. That's why manufacturers included an indicator of exposure in digital radiography. So this indicator has diverse nomenclature and has been cited as detector dose indicators, exposure indicators, exposure index, air karma indicator, or sensitivity. And hereafter, the term exposure indicators will be used. Third is exposure indicators are numerical parameters of the relative receptor exposure or the estimated absorbed dose to the detector, and it is dependent on the receptor efficiency and sensitivity to incident X-rays. And that's why exposure indicators are procured from the mean detector entrance exposure, which is derived from the mean pixel value within the anatomical region of interest in the acquired image. It also depends on the tube current. And so the total detector area irradiated, the beam attenuation, and patient's composite attributes. Next bullet is, well, noise results from insufficient photons reaching the imaging receptor, and acceptable noise levels are indicative of the image quality. And that's why exposure indicators are proportional to the signal to noise ratio squared, or SNR squared, here on the PPT. And it stipulates the acceptable noise levels. Next is, well, the purpose of the exposure indicator is to determine if the optimum exposure technique was used to acquire the X-ray image in digital radiography. And also it acts as a safeguard against overexposure in digital radiography and computed radiography. It's because overexposure may be curtailed if exposure techniques used produce an exposure indicator within a predetermined exposure indicator range for a specific projection. And next is, without the exposure indicator, verification of the appropriate exposure factor selected by the radiographer is impossible. That's because the predetermined range will be recommended by the equipment manufacturer. However, the range may be further tailored by the radiology department. So according to their image quality, it needs for specific projections. And lastly is consideration of the exposure indicator obtained. A presence of quantum mottle or saturation in the X-ray image, and the various factors that influence the EI will be needed to make informed exposure techniques decisions that upholds the ALARA principle in digital radiography. It's because exposure indicator is the only objective indicator of optimum exposure technique, because digital radiography and computer radiography has the ability to disguise overexposure. In conclusion, the exposure index in digital radiography has been used to indicate the relative speed and sensitivity of the digital receptor to incident X-rays, and ideally to provide feedback to the technologists regarding the proper radiographic techniques for a specific exam that achieves an optimal image in terms of appropriate quality and corresponding low dose to the patient. Currently, because of the many proprietary and distinctly different ways of determining and reporting the exposure index by the manufacturers of digital radiography equipment, there has been confusion regarding use of this value from the technologists, radiologists, and physicist communities. Therefore, an effort to standardize the EI for all digital radiography detector systems was initiated by the International Electrotechnical Commission, or IEC, and the American Association of Physicists in Medicine, or AAPM, with participation by diagnostic physicists from around the world and representatives from many digital radiography manufacturers. But the goals of each group were recently completed with the resultant of IEC standard, which is the exposure index of a digital X-ray imaging systems, which also provides a unified method to generate an exposure index value. And this requires users to input a target exposure index. So target exposure index is a value for each exam, and it indicates a deviation index. So deviation index again is the value that gives feedback to the technologies regarding technique and image quality based on signal to noise ratio. But although these are important values in providing feedback in regard to achieving the optimal images at the lowest dose, the exposure index and the deviation index don't directly indicate patient dose. So what what indicates the patient dose. So dose to the patient is dependent upon many factors, including the parts of the body being examined, presence or lack radiation sensitive organs being exposed to x-rays, the area of the x-ray beam, which is determined by collimation, irradiating the patient. The next is the output of the x-ray tube as a function of kilovolt peak, tube current, and lastly is the exposure time and beam filtration. And there are several ways to estimate the dose to the patient, which are peak skin dose and effective dose, which are the most common. So peak skin dose values are determined from, firstly is measuring the x-ray tube output or the air kerma per milliampere per second as a function of kilovolt peak at fixed filtration and at a fixed distance, and determine incident air kerma to the patient based upon knowledge of the kilovolt peak and milliampere per seconds, and also corrections for variations in distance. Second is using a kerma area product or KAP or reference dose device positioned at the x-ray tube collimator that physically measures x-rays emanating from the focal spot to generate a dose area product or a reference point dose, but either way of which can provide an estimate of the incident dose to the patient. But what is KAP? KAP is a measure of the energy imparted through air by ionizing radiation over entire physical area of the X-ray field. And also, it is the appropriate measurement for total radiation incident on the patient's skin and is an indication for the total amount of radiation imparted during the examination. Next is the effective dose. So effective dose is a calculated value based upon the estimated dose to radiation sensitive tissues and organs in the beam as the sum of the product of fractional estimated dose to organs or tissues times or multiplies their weighing coefficients. Although the exposure index doesn't directly relate to patient dose, the importance of tracking and evaluating the EI and DI values in an effort to ensure correct use of the equipment and to optimize radiation dose on an exam-by-exam basis for appropriate patient care. After learning all of this, let us go back to the main concern, which are the issues. Firstly, CR and DR systems have variable speed, wide dynamic range, and internal signal scaling. Second, consistent image appearance eliminates exposure feedback loop, and also it opens inconsistency. Third is there is no direct link between image appearance and detector speed class. Fourth is the overexposures can easily be unnoticed, resulting in needless overexposure to the patient. And lastly, underexposure have increased image noise that can reduce diagnostic accuracy. Moving on, let us now go through our system indicators. First, let us screen film system indicators. It is a traditional screen film system that use overall film density as an exposure indicator and a direct feedback to the technologies regarding exposure, seen in the graph below. So I'm not really mostly familiar with that as I play, but the x-axis is the exposure and the y-axis is the optical density. So the exposure or the x-axis, it determines whether it is high or low density, while the y-axis is the higher the optical density, the more opaque the region is in the image, and the lower the optical density, the more transparent or the more light is led through the image. And in that slope is the three regions. So at the lower is the toe region, the center is the linear, and the top is the shoulder region. Toe region is called the brightest region because it doesn't get that much x-rays reaching on our screen films. That's why it is called the brightest region of the image. And the regions in the shoulder is called the darkest because the regions of the films as it exposes, it will turn dark on our screen. And mostly the shoulder region is the regions which has more exposure. And lastly is the linear. The linear region provides us a contrast and anatomical detail within our image. But let us not focus on the screen film because right now we'll be discussing about the CRNDR system indicators. So the CRNDR system indicators use image processing to align the grayscale with the signals, and direct visual cues are lost regarding exposure. In computed radiography systems, our dynamic range of this image is much more than our characteristic curve on our screen film. We've got much more specific value for each one of these exposures on our computed radiography cassettes. And we can change the exposure, and also we can change the steepness of the graph, we can change the contrast within our image, and much more than we could do on our screen film cassettes. In screen film cassettes radiography, we are creating an image that we cannot manipulate or alter or enhance after the image is produced. So that's why we need to know the characteristics of the screen film prior taking the X-rays exams. While in digital radiography and computed radiography, once we created an image with grayscale values for each pixel, we can then mathematically manipulate all those grayscale values in order to change the image or enhance the image for better diagnostic. So that's the end of my topic about exposure indicator range. Now we're going to move to the noise. So the image processing adjusts the grayscale. However, images with low signals are noisy, and images with high signal are associated with high dose. Exposure indicators describe image quality in terms of the signal to noise ratio or SNR. And as you can see in this picture, these two images, and the underexposed X-ray have a low signal to noise ratio, while the overexposed have a high SNR. Furtherly, this will be discussed by the next member.
Thank you, Sunshine. Before I start, I am Desiree Heidi Ravidad, and I'm going to explain the next topic of our presentation: computer noise. Noise plays a dominant role in the detection of low-contrast objects in any imaging system until the advent of the computed tomography, scanner, and more recently digital radiography. Noise in an imaging system, typically a screen film combination, was considered to have two major components. The first one, electronic noise. This arises from the inherent fluctuations in electronic components such as amplifiers and detectors during the signal acquisition process. The second one, quantization noise. This occurs due to the discrete nature of digital imaging, where continuous analog signals are converted into discrete digital values. Quantization noise results from rounding errors during this conversion process. Computer noise refers to random variations in pixel values in an image caused by electronic factors such as signal amplification, digitization, and processing. It can manifest as graininess or speckling in the image, reducing overall image quality. Noise ratio, SNR, of the TV camera required significant improvements before digital video and geography with intravenous injections could be implemented. The noise in the imaging chain, which ends up in the output of the system. The final image deteriorates the quality of the final image in both a subjective and a quantitative sense. The signal-to-noise ratio, SNR, refers to the ratio of the strength of the signal, the useful information, such as the X-ray image, to the level of background noise present in the image. A higher SNR indicates a clearer and more reliable image, while a lower SNR can lead to reduced image quality and diagnostic accuracy. Increasing the SNR is a key goal in radiography to improve image quality and diagnostic confidence. These ratios of the digital radiography system were measured using the digital image data recorded in the computer. The major sources of the noise include quantum noise, TV camera electronic noise, quantization noise from the analog to digital, converter, time jitter, structure noise in the image intensifier, and video recorder electronic noise. Electronic noise. Computed radiography. The sensitivity of computed radiographic image plates to ionizing and or non-ionizing radiation, such as light, heat, and scatter. Radiation have been known to cause effects such as electronic noise and to degrade image quality. Electronic noise in computed radiography refers to random fluctuations in the electronic signals generated by the components of the imaging system, such as the detector and amplifier, during the process of the capturing and processing the X-ray image. This noise can be caused by various factors, including thermal fluctuations, imperfections in electronic components, and interference from external sources. It can manifest as background noise or interference in the final image, reducing image clarity and diagnostic quality. Minimizing electronic noise is important in computed radiography to produce high-quality images for accurate diagnosis. Electronic noise refers to unwanted signals or fluctuations that can degrade the quality of the digital images produced. This noise can be caused by factors such as background radiation, imperfections in the imaging equipment, or electronic interference during the image acquisition process. Minimizing electronic noise is crucial for obtaining clear and accurate radiographic images. Effects of image plate storage temperature on dark noise. Image plates from Fuji and AGFACR systems were stored at various room temperatures for 5-hour durations and then processed using their respective system. The temperature at which image plates are stored can significantly affect their dark noise levels. Higher temperatures generally increase dark noise due to increased thermal energy, leading to more random electron hole pairs being generated within the material. This can degrade image quality and reduce sensitivity. Storing image plates at cooler temperatures can help minimize dark noise and preserve image quality over time. The average pixel value in several regions of interest in the resultant images were used as an indication of dark noise. The variation in the average pixel values was used to calculate image noise levels. Result: image plates of the Fuji system only showed significant increase in dark noise and image noise levels when the temperature exceeded 40 degrees Celsius. This approach can help identify areas with higher levels of dark noise, which could be important for image quality assessment or noise reduction techniques. The image plates of the AGFA system showed increase in both quantities at all temperatures. Conclusion: it is recommended that storage temperatures of image plates be kept below 35 degrees Celsius to minimize dark noise effects. The major sources of noise generation in a digital radiography system include X-ray quantum noise, TV camera electronic noise, quantization noise, time jitter noise, structure noise in image intensifier, electronic noise of video recorders, structure noise time jitter interplay, and patient absorption in homogeneities, patient motion. TV camera electronic noise is made up of noise from the preamplifier and beam shot. Noise in the TV camera tube and is determined by the video bandwidth, the design of the TV camera tube and camera electronics. Material model. Noise is an undesirable fluctuation in optical density of the image. Lower noise results in a better radiographic image because it improves contrast resolution. There are two major types: material, no control over, and quantum model, some control over. Material model refers to the distribution in size and shape of the phosphors in the intensifying screen. In digital radiography, the two major types of materials used are amorphous selenium ASE and amorphous silicon ASI. It refers to noise or graininess in the image caused by various factors like scatter radiation, detector imperfections, or processing artifacts.
I am Audrey Pascual, and now let's proceed to quantum model. So what is quantum model? A quantum model is the statistical fluctuation of number of photons absorbed by the intensifying screen to form a light image on the film. And now, as you take a look at this picture, quantum model comes in when you look very closely at this radiograph. Even if it is something that is uniform thickness, when you zoom in really close, it looks like a bit static or gumagalaw siya. And as a quantum model refers to the graininess of the X-ray images or can be described as salt and pepper look. Kung titignan mo yung image sa may screen, meron siyang parang batik-batik na itsura, like para siyang pepper or salt talaga. And it is caused by a random X-ray emission, a limited number of X-ray photons to create an image, and a statistical fluctuation in the number of quanta or unit area absorbed by the receptor. The only strategy for reducing quantum model is the use of more MAS or more photons by using a slower speed system or requiring more MAS or increasing MAS with decreasing kVp. A very fast screen have high quantum model because it takes power X-ray to make the image. And next, we have contrast. So, contrast is the range of density variation among light and dark areas on a radiographic film. Image contrast in radiography is critically important, and contrast, it is how our eyes see the different structure in radiography. And now, take a look at these two pictures in the screen. First two square, they look like a pixel within radiograph. These two square are nearly the exact same brightness level. We call that low contrast because the visible difference is very small. At the second image, first square is brightened and darkened the second one. There is a greater difference in brightness level and it is called the high contrast. Kung iisipin mo, ang low contrast is more on shade of gray and then the high contrast naman is more on black and white color naman. And now, next is this image. This image has a different contrast. The first image has no contrast at all. Kaya ang makikita mo is gray lang. So, no contrast po yan. All structure in this radiograph are the same brightness level. It is all the same shade of gray. And the second image has a low contrast. There's some different in brightness level, but it is very small. Kung titignan mo, meron ng visible image, but more shade of gray pa din. Pero kapag no contrast at all, it is same shade of gray lang. And then the third image has high contrast. They are obvious difference in brightness level between structure, and now here we can see something that we couldn't see in the images, in other images. So, kung i-compare natin siya sa first and second image, yung third image is more on black and white color na siya. Kung i-base natin siya sa sinabi ko kanina na ang high contrast is more on black and white color. Then low contrast is more of shade of gray naman. And the term contrast is closely related to other term like grayscale. That is described as the total brightness level visible in image. A high contrast image has a short grayscale, which means that there are only few shades of gray and a lot of black and white. Parang yung sinabi ko nga kanina na ang high contrast is more on black and white. So, short grayscale lang siya. And the brightness level is very different and easy to see. And a low contrast image naman has a long grayscale. This means that there are numerous shades of gray and very little black and white. Yun nga, mas maraming shade of gray pa kapag low contrast. The brightness level are very similar and harder to see. So, medyo hindi malinaw yung magiging image kung low contrast siya. And then next, we have the radiographic contrast. So, radiographic contrast is the overall contrast in radiograph. So, radiographic contrast is divided into two factors, which is subject contrast and film contrast. First is subject contrast. Subject contrast is the ratio of the number of photons in two or more equal zones of the aerial image. Aerial image is that image that contains the information derived from the patient. And there are determining factors of subject contrast. First is patient size. With increased total thickness of tissue transversed by the X-ray beam, there are more atoms available. Kapag next naman is the density. With higher density, more electrons are present per cubic centimeter of tissue. And lastly, we have attenuating characteristic of subject. Attenuation is higher per centimeter of bone than per soft tissue. And now, we have the film contrast. Film contrast is vary in inherent contrast depending on their emulsion characteristic. Film are designed for long, medium, and short contrast. And film development also affect film contrast. And the relationship between film contrast and subject contrast is that radiopacity is the degree of attenuation in a tissue. Radiolucency is the degree of transmission in the tissue. The greater the tissue attenuation, less radiation transmitted through the patient. Various soft tissue are represented as shade of gray depending on their differential absorption or attenuation. And lastly, ultimately reduces subject contrast, which improve image quality. Contrast influenced by KVP level, subject contrast, scatter radiation, film fog, and film type. And next, we have the recorded detail. So, what is recorded detail? Recorded detail is described as the degree of geometric sharpness or accuracy of the structural lines recorded in the image, also referred to as definition, sharpness, or spatial resolution. The ability of a radiographic image to demonstrate sharp lines will determine the quality of recorded detail. The imaging process makes it impossible to produce a radiographic image without some degree of unsharpness. A radiographic image that has greater amount of recorded detail will minimize the amount of unsharpness of anatomic structure line. The amount of recorded detail is controlled by minimizing geometric unsharpness and receptor unsharpness and by eliminating motion sharpness. It is typically measured in the line pairs per millimeter. Next are the factors affecting recorded details. First is focal spot size. The size of the focal spot on the anode of the X-ray tube profoundly influences the recorded detail. A smaller focal spot size yields superior spatial resolution, enabling the depiction of finer anatomical details. Increased focal spot size decreases recorded detail, and the increased source film distance increases the recorded detail. Next is the object film distance. When it increases, the recorded detail decreases. And the receptor speed, if it is increases, the recorded detail decreases also. And when the screen speed increases, the recorded detail decreases. And the motion, when it increases, the recorded detail decreases also. The patient motion during image acquisition introduces blurring and compromises recorded detail. Techniques such as immobilization devices and shorter exposure time mitigate motion artifacts, preserving image sharpness.
Good day, everyone. I am Ayana Ashley, your next reporter. Radiographic artifacts. An artifact is any unwanted image on a radiograph. Artifacts are detrimental to radiographs because they can make visibility of anatomy, a pathologic condition or patient identification information difficult or impossible. Any type of improper handling causes artifacts. Artifacts are marks that sometimes appear on the processed radiograph. Radiographic film is pressure sensitive, so rough handling or imprint of any sharp object is reproduced on the processed radiograph. Creasing the film before processing produces a fingernail-appearing artifact. Dirt, on the other hand, or on intensifying screen results in spot artifacts. Artifacts can be classified as plus density and minus density. Plus density artifacts are greater in density than the area of the radiograph immediately surrounding them, and minus density artifacts are less density than the area of the radiograph immediately surrounding them. Some common plus density artifacts not caused by processing. Half moon marks. The cause is a bending or kinking of film. Example po dito is kapag naglo-loading and unloading po tayo ng film sa cassette ay nakukurot ang film pag nag-unload and loading. And kapag yung kuko is nadiin sa film, nagkukos po siya ng half moon marks. Next is scratches and abrasions. And the cause is a fingernail or other scratches. Static discharge, and the cause is a sliding film over flat surface. Fogging, and the cause is a exposure of white light, ionizing radiation, heat, safe light fogging, and expired film. Some common minus density artifacts not caused by processing. Fingerprints. The cause is a moisture on finger transferred to film before exposure. The second is a scratches abrasions. The cause is a scraping or removing emulsion. Foreign objects, and the cause is some unintended objects in the imaging chain. Last is the non-specific density decrease, And the cause is the dirty screens or cassette. And the patient is any recipient of healthcare services that are performed by healthcare professionals. The patient is most often ill or injured and in need of treatment by a physician, nurse, optometric, dentist, veterinarian, or other healthcare provider.